Hello and welcome to this video on LTSpice. Today we will see the dependent sources and an introduction on the two-port networks. We will start with the use of the dependent source, then continue with a quick theory on the two-port network. Afterwards, we will do an exercise to understand this theory, and this will be the biggest part of the video. Finally, we will see how to replace the dependent voltage source in the two-port network with a dependent current source, and I will also give you an example to underline the importance to check the experimental results. We will see 6 dependent sources. For each of them you have its name and symbol to find it in the LTSpice list of components. In this example, we consider this circuit with the voltage on A equal to 1 volt and the current equal to 0.1 ampere. Let's have a look at the voltage dependent voltage source. Here we have the voltage reference and here the voltage gain, and if I run this circuit, the voltage here is equal to 2 volt. The second one is a current dependent voltage source. The configuration is the following one. At first, we have the name of the voltage source, of which we consider the current, and then we have the trans resistance between the voltage and the current. So run. We look at this voltage and we can see that we have minus 0.2 volt. So why? Because if we look at the current probe on the voltage source V, the current probe is in this direction, and this current is negative. So that's why we have here minus 0.2 volt. So be careful with the positive direction of the considered current. Then it is the same logic for the two following sources. And finally, we have the arbitrary behavioral current and voltage sources. So for the current source, here we enter an expression for the current, and here in this expression we have a voltage and a current, but LTSpice will process automatically the units. So here, for example, the current is equal to 2.2 ampere. We will do a quick theoretical part to show you that the exercise we will do is theoretically available. Here we have a two-port network, or also called a quadrupole. This is an electrical circuit element with 2 ports. And for a port, the current that enters a terminal is equal to the current that goes out from the other terminal on the same port. The aim of a two-port network is to isolate and analyze a circuit. It is like a black box. If we have a linear and sinusoidal circuit, we can use the complex. Here we will be interested in the current and the voltage on the ports. A way to link them is by means of this matrix with 4 impedance parameters. And then we obtain 2 equations, and those equations are equivalent to this circuit, and thus this circuit is equivalent to the circuit inside the two-port network. Then Z11 is equal to U1 out of I1 when I2 is equal to 0. And so on for the other parameters. Here we have the representation of a two-port network in a circuit with on the left a source represented by its Thevenin equivalent circuit and on the right a load represented by its input impedance. For the two-port network, we have three parameters. Zin is the input impedance and is equal to U1 out of I1 and equal to this if you know the impedance parameters we have seen. Zin is the impedance seen at the input when the output is loaded by an impedance. Then Zout is the output impedance and is equal to U2 out of I2, or also equal to this. And this is the impedance seen at the output when the input is closed by the impedance of the source. So it means that when US is equal to 0, so replaced by a wire. And finally, U2O is equal to this and is the open circuit voltage. And now we will see a way to calculate these three parameters. Here is the circuit we will analyze. On the left, we have a sinusoidal source with its series resistance. On the right, we have a load, and in the middle, a two-port network. In the two-port network, you maybe don't know this circuit, but it's not a problem. The aim here is to show you that a quite complex circuit may be condensed in an easier one. I will present you the idea of this circuit, but if you don't understand, it's not a problem for this video. The important will be the conclusion. This circuit is designed such that when we apply a sinusoidal signal on the left, we can study the circuit by representing it like this. So here we have a resistor, here the ground, and the two transistors here are now two resistors and a linear current source. Thus, the conclusion is that this two-port network is a sinusoidal and a linear circuit. And as this two-port network is in a circuit like this, so with on the left a sinusoidal source and on the right a load, so we can represent this two-port network like this. Furthermore, as we have no capacitor and inductor, the impedance of these elements is resistive. So we have only resistors. So here we have the equivalence circuit. U2O is a voltage-dependent voltage source controlled by the voltage U1. So now we have to find R in, R out, and AV, the voltage gain between U2O and U1. To establish the voltage gain AV, we remove RL. So on the right side, we have an open circuit and U2 is equal to U2O. Then we can write this, and AV is equal to U2 out of U1. Let's analyze this on our circuit. So RL is removed. And we obtain this. V2 out of V1 is equal to minus 188. And we could also find a cutoff frequency in the high frequencies. This is due to parasitic capacitance of the transistors, but we won't get interested in this, and we will only consider the frequency interval where we don't have this effect. To calculate Rin, we simply use that Rin is equal to U1 out of I1. Notice that here we keep RL when we measure Rin. Let's do this measurement. So V1 out of I1, so the current in the resistance Rs, is equal to 14.2 kilo ohm. As said in the theoretical part, when we calculate Rout, we first have to replace Us with a wire. This involves that U2O is equal to 0. This result is very useful for our calculations. We could determine Rout with U2 out of I2. But we will see another way to calculate it, and we will use the resistive voltage divider with a Rm resistor we will add to the circuit and Rout. So we can consider this formula, and Rout is equal to U2 out of Um minus U2 times Rm. And in the case where Rm is equal to Rout, we have U2 equal to Um out of 2. So here we have the circuit configured to calculate Rout. And let's look at the green curve. So we have V2. So V2 is equal to this, and Vm is equal to 1, and Rm equal to 5 kilo ohm. So we can use this formula to calculate Rout, and we find that Rout is equal to 9.1 kilo ohm. In red, we have V2 out of I2, and we can confirm that Rout is equal to 9.1 kilo ohm. Now we can enter the values of the parameters we've calculated in the right two-port network and compare V2 of both circuits. And we can see that we obtain the same result. So both two-port networks are equivalent in this circuit. Let's do a quick analysis of the result. As Rin is larger than Rs, U1 will be equal to Us. Then U2O is equal to minus 188 times Us in this case. And as Rout is equal to RL, U2 will be equal to U2O divided by 2, so minus 94, and that's what we have here. And this is another way to confirm that Rout is equal to 9.1 kilo ohm. Let's take RL equal to 100 ohm. We still have the same result for both circuits. The equivalence seems to work even with another RL in this case, but the gain is very small. Here we have 2 volt at the output for an input of 1 volt. Before we had an output of 94 volt. So why? Because if we take the resistive voltage divider and then we say that R out is the R1 here, then RL the R2 here. If R1 is larger than R2, U2 will be attenuated, and we don't want this in an amplifier. So in an amplifier, we will prefer a small R out to have this U2 quite equal to this U2O. Then in an amplifier, we also prefer a big AV here, so it's logic, and a big R in, because let's take RS is R1 here and R in is R2 on the left page. If R in, so the R2 is bigger than the R1, the voltage here will be quite equal to the voltage here, so we will have a better signal then to transmit. I just want to add a comment. We have used an AC amplitude of 1 volt for the directive point AC. But then, when we use the point 1 directive with an amplitude of 1 volt, we can see that the linearity is broken. And we have to take a smaller amplitude, here for example of 10 millivolt, to have the linearity we've used to build our two-port network and to obtain the results we've calculated. But the results with the directive point AC for an amplitude of 1 volt were correct because this directive seems to maintain the linearity of the devices. In this two-port network, we have a voltage-dependent voltage source. It is also possible to represent this two-port network with an equivalent current-dependent current source that is controlled by the current I1. To do this, we will use this equivalence between a voltage source and a current source you have seen in class. The R out in series with the voltage source is the R out in parallel with the current source. Then we can use the equivalence. So U2O is equal to I2O times R out, and U1 is equal to R in times I1. We can then combine these equations and we obtain AI is equal to this and is equal to minus 293.4. On the left, we have the circuit with the voltage-dependent voltage source, and on the right, the circuit with the current-dependent current source. Here we have V because the current that we consider is the current in the voltage source V. And here, the current gain we've calculated, but notice that there is no minus because the current in the voltage source is equal to minus the current in the resistor R in, so minus I1. And here we can see that we have the same results for both circuits, so it means that both circuits are equivalent. When you do this kind of experiment, it is generally better not to get satisfied of only one result, because sometimes we may have some surprise. For example, if we try to calculate the input resistance with this technique we've already seen for the output resistance, Rm will unbalance the symmetry of the circuit in the two-port network and modify its properties and its input resistance. We use this if U1 is equal to U1 prime divided by 2, then Rm is equal to Rin. And we obtain this result for a Rm equal to 20.8 kilo ohm, and this is not correct with the 14.2 kilo ohm we had calculated. But now, if we do this, we can use both formulas here, then combine them, and here if U1 is equal to U1 prime divided by 2, then Rin should be equal to 2 times Rm. So let's try this. And here we can see that for Rm equal to 7.1 kilo ohm, U1 is equal to U1 prime divided by 2, so Rin is equal to 2 times Rm, so to 14.2 kilo ohm. So we obtain here the good result because the symmetry is maintained. So it is important to be careful with this and always compare your result with other experiments or with the theory.